For decades, the integrated development environment existed as a single, monolithic application. You write the text, the editor compiles it. Xcode 27 marks a shift where that unified logic is divided. This update transitions the IDE from a passive text editor into an active, agentic harness. It is a modular architecture designed to do more than just host your code. This shift addresses a persistent engineering trade-off. Developers require the instant response of local processing for typing, but need the high compute reasoning of massive models for multi-file planning. The architecture formally separates the workload into two nodes: Tier 1, which executes on device, and Tier 2, which routes tasks to the cloud. We are going to deconstruct how Apple routes data between these tiers, specifically looking at how the Agent Client Protocol and Model Context Protocol bridge the IDE and external agents. Then, we'll analyze how these protocols combine to allow agents to compile, run, and visually verify their own code. Understanding this architectural separation is necessary to utilize the full scope of modern AI-driven development. Effective coding requires a flow state, where there is no perceptible delay between a keystroke and the editor's response. Tier 1 is the layer designed for these immediate interactions. It is a purely on-device execution path powered by your Mac's own silicon. This node relies on the Apple Silicon Neural Engine to handle inference requests without sending data over a network. Because the compute is local, it offers three specific guarantees: zero latency, total data privacy, and a scope limited to the single file you are currently editing. Tier 1 handles tactical tasks like inline autocompletion and generating local documentation. However, the neural engine has physical limits regarding context window and raw power. It cannot analyze a dozen interconnected files to perform a complex, project-wide refactor. Local inference provides speed for line-by-line editing, but it cannot manage macro-level system design. When a task requires high reasoning or multi-file awareness, Xcode must look beyond the local hardware. This leads to the second node, Tier 2. This is the routing mechanism for cloud-based reasoning engines. Standardizing the communication between the IDE and these external agents is a new standard called the Agent Client Protocol, or ACP. ACP creates a standardized bidirectional bridge that lets external agent harnesses talk directly to the Xcode editor. By using an open protocol, Xcode avoids locking developers into a single proprietary intelligence model. You can route tasks to various third-party engines, such as Claude 3.7 Sonnet, Gemini 2.5 Pro, or the Cursor Composer harness. Setting this up involves pointing Xcode to your agent's path and using ACP as an execution argument in the system settings. ACP allows you to switch between different reasoning engines to find the best fit for a specific architectural task without leaving your development environment. These cloud agents enable a different workflow. Rather than starting with raw code, you can use the /plan command to establish structural constraints first. In this /plan output, the agent defines architecture using Swift 6.4 concurrency features like @observable and @mainActor before a single line of logic is written. To move from planning to execution, Xcode utilizes another standard, the Model Context Protocol, or MCP. While ACP manages communication with the editor interface, MCP is what grants the agent permission to use actual tools. When you enable the MCP toggle, you are unlocking the agent's ability to reach back into your system to use the native toolchain. MCP gives the agent direct read and write access to the compiler, the test runner, and the simulator runtimes. This transforms the LLM from a text generator into a participant that can build and run the software it designs. Even if code compiles, it still needs to be verified on a device to ensure the user interface functions as intended. Xcode 27 introduces a unified DeviceHub and native MCP tools to automate this verification loop. The agent generates the code, calls the compiler tool to build it, and then launches the app in a simulator. The agent can then simulate swipes or taps, take a screenshot of the result, and analyze that image to validate the UI. This autonomous loop requires a vision-capable Tier 2 model that can ingest and interpret those screenshot images. A model without vision capabilities, like GLM 5.2, cannot process the visual feedback, causing the automation to stop at the validation stage. Developers can choose between using native Xcode tools or third-party MCP servers for these automations. Native Xcode tools are precise, but they operate by spinning up specialized subagents for each individual tool call. This subagent approach requires significant context to be passed back and forth, which increases the total token usage for each test. While autonomous validation provides precision, it moves the primary engineering cost from manual testing time to API usage. When these two tiers work together, they form a complete orchestrated ecosystem. The full data flow, local interactions start on the neural engine, while complex reasoning routes via ACP to the cloud, using MCP to control native tools. The system moves from a plan prompt to a verified app without a human launching a test. The strength of Xcode 27 is found in this handoff. It combines the speed of local silicon with the deep reasoning of cloud agents through standardized protocols. By standardizing how agents communicate with the editor and the toolchain, Apple has linked code generation directly to functional testing. This setup creates a continuous loop where the environment can build and verify software at the speed of the models themselves. Understanding how to configure this dual-tier architecture is now a central skill for developers looking to maximize their efficiency in the iOS ecosystem.